Hello and welcome to Golden Geography. Today we're going to be looking at Earth's life support systems, which is part of the OCR Geography A-Level specification. We're going to be focusing on key question 3, which is how much change occurs over time in the water and carbon cycles. And there's 2 sub-questions for this that we will be looking at. We're going to start with 3A, which looks at human factors and how they can disturb or enhance the natural processes and stores in both the water and carbon cycles. So first of all, we need to think a little bit about dynamic equilibrium in the cycles. Dynamic equilibrium is where you've got your inputs and your outputs, and they may change, but they change together. So if you have an increase in your inputs, you have an increase in your outputs. Therefore, you have change, it is dynamic, change is happening, but your system is still in balance or in equilibrium. So if you think about a glacier, and this is a really good link to the glaciation unit we looked at, if you think about a glacier, if there's more snow building your glacier, then you need to have more ablation, more melting of your glacier. So you have an increase in your inputs, increase in your outputs. So it means you have change, but that change is in balance. That can happen on a short-term basis, so it may be on a daily basis or seasonally. And it may happen over a much longer period of time, decades, millennia. When we're looking at what maintains equilibrium, we need to think a little bit about feedback cycles. And we have effectively 2 types of feedback cycles. We have positive feedback cycles and negative feedback cycles. On the whole, positive feedback cycles, even though it's got the word positive in it, are actually bad. They lead to changes that take you out of balance or out of equilibrium. Whereas negative feedback cycles will bring you back into balance and equilibrium. So we'll have a little look at these for the water and carbon cycle. If we think a little bit about the water cycle first, we can see that if we have rising temperatures, then we get increased evaporation, which means we have higher humidity, we have more water vapour in the atmosphere, which means we end up with higher temperatures because water vapour in the atmosphere is a greenhouse effect, a greenhouse gas. So we get higher atmospheric temperatures, which means we've got rising temperatures. So you can see from the water cycle, it's a positive cycle, it's getting worse, right? We've got change that's making it worse. If we look at the carbon cycle, again, it's a positive feedback loop here. Again, it's making things worse. We've got rising temperatures at the top. Then we have melting of tundra. As we've got that warming of the tundra area and the melting of the permafrost, then we get the release of methane. That release of methane into the atmosphere then increases those atmospheric temperatures, which then cause that positive cycling, things getting effectively just worse and worse. So both the water cycle and the carbon cycle can experience positive feedback loops, which means that actually the situation is coming out of balance or out of equilibrium. And we are seeing that globally at the moment with climate change, particularly in the northern hemisphere, where temperatures, because of methane and what's happening in the tundra, are getting much higher, much quicker, those atmospheric temperatures. So positive feedback loops take things out of equilibrium. We do also, however, have negative feedback loops. We have those for the water cycle. So where we do have rising temperatures, we get increased evaporation, we've got higher humidity. That can generate more cloud cover when it in itself can block out some thermal energy from the sun, and then that can change the atmospheric temperatures so that actually the temperatures reduce a little bit. Here, this is where the concept of loops or cycles fall down, because actually this little section here that links the last two bits together is inaccurate. It should really not be there. It should really be more of a link away, going back to more of an original state. And that's the same for our carbon cycle. We can see we have rising levels of atmospheric CO2 that can stimulate photosynthesis, which is carbon fertilization that draws carbon out of the atmosphere, which means it is stored in our biosphere and our plant life. So this bit shouldn't really be there. It's not really a cycle or a loop when you're looking at negative systems. So again, that doesn't work. Really, we should be looking at this going into a different system. So negative feedback loops are good because they draw the system back into balance, back into equilibrium. Well, we need to think a little bit about what triggers some of these changes, particularly those positive feedback loops. What causes those? And a lot of the answer to that is us. We are the causes on the whole for some of these changes. And it's how we as human beings create something called disequilibrium. We're taking both the water and cycle out of equilibrium. We've done that through land use changes, farming, forestry, and that has changed some of the flows and stores. So here we have a little table that shows us some of the impact of our human activity or the anthropogenic activity. We have urbanisation. Well, as we build our cities, we use a lot of concrete and tarmac that makes our surfaces impermeable. That reduces infiltration. It changes how we have surface runoff. The amount of surface runoff leads to more risks of flooding, less recharge of the water in the groundwater. And similarly for the carbon cycle, loss of vegetation. Producing that cement has impacts. Similarly for farming, it has impacts on both the water and the carbon cycle, taking it out of equilibrium. And again for forestry. So pause the video for a minute and have just a little look at those. When you come to forestry, you'll find it has both deforestation and afforestation. Afforestation is a bit of a management technique. It's good, but it does have its limitations. It takes a long time. Here again, we want to think about human activity or anthropogenic activity and how it's impacting our water and carbon cycles. And one of the key issues we're having as we look to the future with climate change and warmer conditions are issues with sources of water, particularly where we get our water from. And in the UK here, a lot of that is based on water extraction, taking water out of our rivers or out of our groundwater, and that has consequences, particularly for the water cycle, but also for the carbon cycle. So if we extract water for surface areas from rivers and lakes and reservoirs, well, that will reduce the water in those surface areas. It will impact river discharge. It will look at impacting the evaporation from those water bodies. It may have impacts on vegetation and soil moisture for the carbon cycle, and therefore affect the effectiveness of the carbon cycle, and particularly those links with the biosphere. Groundwater extraction, well, that will impact the water table. It will lower the water table throughout the year. It could cause subsidence. It will have an impact on the base flow in rivers. And when we're looking at the carbon cycle, it will put stress on the soil moisture, particularly if you're trying to extract water. It's going to use a lot of energy. It's going to use carbon to produce that energy. Again, human activity, combustion is going to have an impact, this time particularly on our carbon cycle. We've talked about this briefly before, but if we are trying to get oil and gas out of the ground or out of the ocean, the rocks beneath the ocean, sometimes it can be very difficult and expensive, and one way to reduce those costs for businesses is to flare off the excess gas. That burning, that flaring that you can see here is going to generate carbon dioxide that goes into the atmosphere and takes the carbon cycle out of balance, out of equilibrium. But equally, combustion, cars, transportation, within our homes, to heat our homes, for cooking, all forms of combustion, not just flaring, will put more carbon into the atmosphere. And the key thing here is the bottom bit in red. It disrupts that dynamic equilibrium. Well, what can we do about it? This is still relatively new, but we are trying to find out more and more ways where we can sequester that carbon, where we can tie it up, and the diagram shows us some of these. And that would be great. We're trying to help carbon capture by sequestering it, but there are some significant questions that we need to ask, particularly about putting it into the geology. Is that safe? If we're pumping carbon into the rocks, is that safe? Well, what does it do to our flows and stores? We can see here, if we do sequester carbon, well, we're enhancing that kind of natural sequestration. We want to make sure that our biosphere is working and doing that and producing the right conditions for plants to grow. But artificial sequestration too can help, but it is an energy source. Pumping CO2 into gas fields or aquifers does require energy. It will help increase stores, particularly our biosphere, our biomass. If we can get that as a natural flow, it will increase those stores. But absolutely, we need to get the carbon out of our atmosphere. So we need to find stores elsewhere, not in our atmosphere. And again, the bit in the red is really key. If we can do this, if we can find a way to do it better, it will help restore that equilibrium. Okay, key question 3b. The pathways and processes which control the cycling of water and carbon over time. So we want to think a little bit about changes to the water and carbon cycle. And we're going to start with the water cycle and looking at daily changes. And we can see that in this graph. If you were to put a line of best fit and change it to a line graph, you might be able to read it a little bit better. But really, we're looking at the little dots in the middle here, these little dots in the middle. The rest are variation bars, so don't worry about those too much. But if we draw a little line of best fit here, we can see there are variations. You've got water at the side, we've got time along the bottom. So very early in the morning when we're all asleep, we have very little moisture in the atmosphere, very little evaporation. But when the sun comes up and it is our daytime, that evaporation increases. So we have more water vapor in the atmosphere. And then as we go into our evening, it decreases. Well, what about the carbon cycle? Carbon cycle kind of does the opposite. At night, carbon levels in the atmosphere are quite high. And during the day, we find that they drop. So if we look from about 6 o'clock onwards, as the sun comes up and plants start to photosynthesize and capture that carbon, then the carbon levels in the atmosphere drop. And then in the evening, when plants start to stop photosynthesizing, then the carbon levels increase. So on a daily basis, we see changes within our water and carbon cycle. What about seasonally? If you look at a climate graph, we can see those variations for the water cycle. We can see the bars that are the rainfall, and we can see temperature within the line graph. And clearly we have seasonal variation. We know that it rains here in the UK a lot more in the winter than it does in the summer. So we have seasonal changes. That ties into the climate that we experience due to our latitude and longitude. It is a reflection of the temperatures that we have. So in the summer, we've got much higher temperatures and therefore we get more evaporation of water. It's a reflection of the sunlight, the solar energy that's needed for those temperatures and that evaporation, and also of our foliage. So the plants that we have, they are using that water more in the summer months than in the winter. And if we look at the carbon cycle, again, we can see these seasonal changes. Very much here in the northern hemisphere, we can see peaks and troughs. So those troughs happen in our summer when the plants are photosynthesizing, when they're using up all that carbon. the amount of carbon in the atmosphere declines. As we head into autumn and winter, those plants, some of them will drop their leaves, others that are annuals will totally decompose, and that decomposition is releasing CO2. So we find not only decomposition but also lack of photosynthesis leads to an increase of CO2 in the winter, and it cycles through. So again, location, latitude will impact your climate. The temperature between winter and summer and how that influences our photosynthesis and the vegetation is really important. We also need to think a little bit longer though. We need to think about long-term changes, and this is predominantly thinking a little bit about ice ages and warm periods, what happens to the water and carbon cycle during an ice age and a warm period. And they are linked, as you can see in this climate graph. So here we've got hundreds of thousands of years, and we can see when we have temperatures that are high, then we tend to have high levels of carbon dioxide. And when temperatures are low, we have lower levels of carbon dioxide. So there is a distinctive link between carbon dioxide and temperature. Scientists do debate which is the leading factor though. Most think changes in carbon dioxide in the atmosphere lead to atmospheric changes. There is a little bit of debate. But there is a definite pattern between the two of them. So what does that mean then for our water cycle? Well, obviously during ice ages, the majority of water is trapped or stored in the ice, and that affects other stores. So the water stored in our oceans decreases. We have lower sea levels. We have less water in our atmosphere, so we have lower levels of precipitation. Even though it's cold, you don't get as much snow during an ice age as you would do during a warm period. And that is really important. Well, what about carbon cycle? Carbon cycle is reflective in that. So you will find that climatic changes will be reflected. So during those ice ages, carbon levels are much lower. There is less plant life, there is less photosynthesis, there is less decomposition. But actually there are a few other factors that influence the carbon cycle on a longer term scale. Tectonic activity is really key. The amount of carbon in our oceans, which again links to the amount of water we have in our oceans, can play a part too. So feel free to pause the video and have a little look at this. Okay, so if we have changes in the water and carbon cycle, both on a short-term and long-term basis, that's going to impact us. We need water and carbon. Go back and have a little look at the videos for key question 1. They are absolutely essential for life on Earth, and we use them and utilise them. So we need to know what's going to happen to them, and that involves understanding patterns of the past, but also patterns of the future. We need to monitor them. We need to find out how much carbon is where is it stored, where could it be stored, how is it moving between one store and another, and the same for the water cycle. We need to monitor it, we need to research it so it can influence our governments and some of the policies and agreements that they come up with. So here we have for the water cycle a few key things that are done. NASA, I'm hoping you've heard of them, American, have lots of satellites. It helps us monitor through the use of satellite imagery where some of our water stores are. We have gauging stations, ice core analysis, soil moisture sensors too, all of which can tell us a little bit about the amount of water stored, but also its transition in and out of those stores. They are important, but here you need to do a little bit of analysis. Does this tell us everything about every bit of water around the world, or just about one particular place? So is it a local or global technique? Is it a short-term technique? Is it giving us information now and for the next 3 days, 5 days, 7 days? Or will it give us much longer-term information? And here we have the same for the carbon cycle. We can and do have lots of information from the Mauna Loa Observatory. Again, we can use satellite remote sensing and sediment and ice cores. They are really useful at telling us about carbon fluctuations. But think about that analysis again. Local, global. Where are these bits of information coming from? How applicable are they? If you're looking at Mauna Loa, Hawaii, does that tell us about the UK? Possibly. Possibly not. What is it telling us? Is it long term or short term? So try to analyse this data too. And do some more research. Feel free to Google them and find out more. Okay, so time to review. Pause the video, have a little look at these key points. Green, you get it. Amber, you need to review. Red, I need some help. Thanks for listening.